Let's get started with the next one here. The topic is Integration of Analog, Microcontrollers, and Control Theory in Senior Design by Professor Beauchamp from University of Puerto Rico, Mayaguez.
Should we start? Okay. I did this with two students, undergraduate students, as undergraduate research project, and also with Dr. Manuel Jimenez, who couldn't be here today. What we did was we used a system that is called the ball and beam system. It's a use in control system as an educational tool. And we built a controller using the MSP430. So our lab, there is another lab, it's called the Microprocessor Interfacing Lab. It's the Dr. Jimenez lab. It was founded in 1989 with institutional funds and also has been maintained through industry and UPR funding. And it serves in the order of 120 students, computer engineering and electrical engineering seniors, and it teaches embedded systems design using the MSP430, Luminary Micro, TMS 330, and others. And the project cycle is the students have to come up with a problem. They have to specify the problem they want, and they design the system and build a prototype and have a demo, and that's the end of the cycle. So it's a semester-long project, and it's open in that sense. And the lab that I am presenting today is the Process Instrumentation and Control Lab. It was founded in 1992 through an NSF Instrumentation and Laboratory Improvement Grant. It has been enhanced through public funding, serves in the order of 200 students a year, and 2 graduate courses and early stages, and this is what we are emphasizing here. In the early stages, we use PCs, National Instrument Data Acquisition Cards, LabVIEW, and since 1998, we've been using Quantum Consulting Data Acquisition Cards and WinCom modules and MATLAB and Simulink implementation. Now, the difference here is that with the Quantum Consulting WinCom modules, you can program in Simulink, and this program, the WinCom program, is just a program that makes an executable program from the Simulink diagram. Okay? And the project cycle in this lab is we start with modeling, so they have to write the equations, and if it's nonlinear, linearize it, design a controller, simulate it first in Simulink. If it works, then they go to implementation and demonstration. So the traditional approach, the way we started was we used, as I said, the PCs and the data acquisition boards and MATLAB and Simulink implementation. And this is good because it avoids signal conditioning issues, microcontroller programming, and difference equation algorithms. So we concentrate, in this case, in the control theory. We don't concentrate much on the circuits and microcontrollers. However, that is good for beginners control course, but for the senior control course, they need to understand better these topics here. So that's why we are trying to do it now with a microcontroller. So the alternative now is to use the microcontroller-based platform. We're using the MSP430 experimenters board. It has an analog front end, 12-bit digital analog converters, and 12-bit and 16-bit analog to digital converters. It's friendly interface programming. Requires analog and signal conditioning circuits for interfacing analog sensors. The thing is that sometimes the outputs of the sensors are not compatible with the inputs of the analog to digital converters, so you need to what we call signal condition the signals from the sensor. also requires dealing with microcontroller programming and different equations. So they actually are doing the programming of the system. The ball and beam system is well known to control people. It's just a ball rolling on a beam, and it is controlled by a motor that tilts the beam, and the objective is that the ball is on the center of the beam. And there is also a master ball that you can move with your hand, and the slave ball is supposed to follow that. The analog part here is these two sensors are potentiometers and are analog sensors. And there is an optical encoder to measure the position of the motor. So that's a schematic diagram of what's going on there, and with all the geometry and angles and all that. And this is a block diagram of the system. The plant is just a servo motor and the dynamics of the ball, and the optical encoder as a sensor, and another position sensor over here. So there is a signal conditioning part here that we have to build with analog systems. And this part is implemented in the microcontroller, which is the actual controller. We have a two-loop system. It's an internal loop for controlling only the motor. So this is a proportional only control. And there is an other loop outside to control the ball itself. And this controller here is a phase lead controller. It can be lead lag, but it's actually phase lead. So the hardware, the way it's organized, is a microcontroller, the digital to analog converters, the digital inputs, and analog to digital converter inputs, and signal conditioning circuit, and we have a power amplifier for the motor, and the optical encoder is fed through the digital inputs, and the potentiometers are read to the analog to digital converters. So the students had to do some attenuator circuits for the potentiometers because they go from +5 to -5. They have to attenuate it and to make it, I think it's 2.5 volts, the input of the microcontroller. Same thing has to be done for the slave potentiometer, and this is the analog to digital converter to the amplifier. So they need to shift it over, 1.25 volts, and it's 4 times the voltage that we need, because the motor works with a -5 to 5 volts, so we have to convert to that. And this is a chip. I don't know if TI makes one similar to this. It's a chip that gets the quadrature optical encoder output and gives you the counts and the direction of the rotation, so that we use to input the microcontroller with the counts on one side and then the direction on the other side. That's pretty much the flow chart of the starting. Configured all the ports, and if there is a button, if you press it, then it starts controlling the system. And this is the interrupt subroutine algorithm. And the results, I don't know if you can see them very well there. The results were better than we expected in terms of the performance criteria that we used were settling time, overshoot, and it was better than we were expecting. And actually, it worked better with the microcontroller unit than it worked with the two different things. This design was done with analog design, and the controller was transformed using the BLT, the bilinear transformation. And this design was done directly in the C domain, so directly in the digital domain. So we could control the ball and beam system. We used both BLT and C transform to design the phase lead. We're able to produce the desired response characteristics. And of the two compensators, the best that performed was the C transform. The reason is that if you design directly in the C domain, that is what you are going to implement with the difference equation. So it's not surprise that it works better with the C transform. The other one is just an approximation, and you have to sample very fast for it to be to emulate what you do in continuous time. Okay. MATLAB and Simulink are good and suitable for advanced and introductory courses because it makes the implementation easier. So it's like the system is there, and the students just need to program, to design a controller and put it to work. However, the microcontroller approach adds new dimensions, and the new dimensions is they get involved into signal conditioning, programming the microcontroller, and using digital control and difference equations. So they actually need to go into the difference equation algorithms. When we started using LabVIEW so many years ago in the early 90s, LabVIEW didn't have so many of the boxes that they have now, and the students actually had to do the programming of the difference equations. But now Simulink and LabVIEW have all these boxes, so they don't get to understand that until they have to program it itself. And if we get into this approach, our lab will benefit very, very much. Okay, that's it. I wonder if there are any questions.
Any questions?
Yes.
Sorry. When you do the Z transform versus the phase difference, do the students get to see kind of compare? Do all the students get to do that the different ways, or do different groups do it that way, or do they get to see the difference between the approximation versus the Z transform?
This is like we're starting to do this. So we did this with 2 students in an undergraduate research project. But the idea is that they understand the difference between designing directly in the C transform domain or in the C plane, and versus designing first in the continuous domain and transforming to the C domain. The idea is that you will need a higher sampling rate for that to work, and in the vocabulary of the students is an overkill, right? So and also, so it's not as necessary to do that. But otherwise, if you don't have the knowledge of the C transform domain, then that is good. That's good enough. But then you still need to sample faster than usual.
And I see that as a valuable learning experience because I see that comparison.
Yes. Actually, we got a paper accepted at the Frontiers in Education conference coming up in October, and we're presenting the results on that comparison. Anybody else?
Any other questions?
Not too many people know controls here, right? I'm sorry. I think it's important, though. That's why I'm here. I think so. You saw a lot of things in the demonstrations today, and I didn't see much about feedback control. I think feedback control is important today. There's so many things going on that are open loop, but I think
the hard thing is, how do you exchange information? So it's interesting to hear what we do at each other's schools, but it stops there, right? So the mechanism, we need some mechanism where content is transferred, like taking it to the conferences is one way. But if we don't go to that conference, not that we don't like control. This doesn't have a good branding mechanism.
Yes. Thanks. Sorry? Okay.
Thank you, Professor Beauchamp. The next presentation will be implementing senior design and how it's being implemented at Oklahoma State University. So we have Dr. Vignesha Damani here for that presentation.
Are you running off today? You can just go on 5 and plug back in.